Hi, everyone. Welcome to Foresight's Intelligent Corporation Group. Today, we have a really exciting presentation by our fellow from the University of Connecticut. And you'll be presenting on a really exciting, mostly cryptography related topic, of which we heard you presenting on already a little bit before at our Intelligent Corporation workshop last year. And some people that were there already have a little bit of kind of preamble to your presentation, but it will be on unclonable polymers and their cryptographic applications. We're really excited to have you on. Thank you so much for joining us. And I'll be sharing a little bit more about your information here in the chat, and I'll be monitoring the chat for your presentation, and then we can hit the road running to the Q&A. But thank you so much for joining us again. It's a real pleasure to have you on. And without further ado, the stage is yours. Please take it away.
First of all, thanks for the invitation and for having me. And let me share my presentation. I'm Ghada Almashaqbeh from the University of Connecticut. And as Alison mentioned, I'm going to talk about my work on building cryptography from unclonable polymers. For those who saw my talk last year, which was very brief, just 10 minutes. So today it is an extended version, and you will get the chance also to ask questions. And please stop me anytime to ask questions. If you don't want to wait until the Q&A, it's up to you. And we can discuss offline, of course, anything that you are interested in. So this is a joint work with my collaborators, Ran, Yaniv, Jonathan, Tal, Itzik, Anna, and Iran. And just to give you a brief background, this is an interdisciplinary work where we combine biology with cryptography. And as you see, myself and my collaborators, we are coming from different fields covering cryptography, computational biology, and biochemistry. And without this interdisciplinary expertise, this work we couldn't do this work. As a motivation, imagine that we have a memory device that is unclonable. And once you retrieve the stored data, this memory device will self-destruct. Furthermore, if this device is storing several messages, only a few of them can be retrieved without having this device fully destructed. Such bounded query memory devices, they are useful in many applications. Among them, we are interested in bounded execution software, which are programs that are secret or have some secret state. And these programs can be executed over only a few inputs. After that, the program will stop responding. Having bounded execution software, as we know, is impossible to achieve in the classic model where we only deal with digital data and digital computational model. And even in the quantum model, it was shown that it is impossible to achieve bounded execution quantum programs without having these special memory gadgets. This idea was put forward by Goldwasser, Kalai, and Rothblum, who showed how to build one-time and k-time programs out of imaginary. They just assume the existence of these memory devices, which they call 1 out of 2 memory devices. So the device stores 2 messages, and you can pick one of them, either the one stored at location 0 or location 1. You cannot retrieve both. And after that, the device will stop responding, or what we call it self-destructs. These gadgets were combined with a notion from the multi-party computation world called garbled circuits to build 1 and k-time programs. And as I said, that work only assumed the existence of these memory devices, and they briefly discussed how to build them by tamper-proofing a whole computation using trusted hardware. And as we know, dealing with trusted hardware comes with side effects, including trusting the manufacturer and assuming that these devices resist side channel attacks and reverse engineering. And clearly, these are strong assumptions and, of course, trust assumptions that we want to avoid. And for this reason, we wondered if we can build these memory devices using alternative technology or hardness assumptions. And towards achieving this goal, we joined forces with top-notch and brave biologists in looking for an alternative technology to build these devices. And these devices must be unclonable and self-destruct, as I mentioned before. And we wanted to do that in a rigorous way, laying down formal foundations and models that will allow us to build provably secure cryptography applications. We wanted to require the minimum on the biology side and have any amplification of the security guarantees and properties on the cryptography side. For this reason, we introduce several cryptographic and algorithmic amplification algorithms to allow us to use these weak memory devices in sophisticated and provably secure cryptographic applications. This whole project, or our request, if you want to call it in this way, is motivated by recent advances in biochemistry that allowed storing data or digital data in the form of DNA. So you take your digital message, you encode it as a sequence of nucleotides that then you synthesize this sequence to produce the DNA material. Reading the data will proceed in the reverse direction, where you read the DNA, you get the sequence, and then you decode it to get your message. Don't worry about the biology details here. Just keep in mind that DNA can be used to store digital data and retrieve that data back. DNA evolved to be clonable. So if you have a sample, you can clone it or produce as many copies as you want of that sample, and this will allow reading the message as many times as desired. So this doesn't work for us. We want something that provides the feature of being unclonable, to have this bounded query feature. And in doing so, we considered another biological polymer, proteins, which can be also used to store digital data. So following a similar paradigm, you encode the digital message into a sequence of amino acids, and then you synthesize this sequence into the protein material. And here, the magic started. First of all, proteins are unclonable. The central dogma of molecular biology states that if you have a sample of protein, you cannot clone it, and you cannot even get the genetic information out of that sample. So in a way, it is easy to go from DNA to proteins, but it is very hard to do the other way around. And this hypothesis or challenge is still standing for 65 years now, and even for billions of years of evolution since this, And to us, this represents a biochemical one-way function. So it is a new hardness assumption. And as cryptographers, we know what to do with hardness assumptions. Basically, we turn hard lemons into lemonade. We build new cryptographic primitives and applications from this new hardness assumption. And this is basically what we did in this work. Another feature of proteins is that reading or sequencing a protein, which is to identify the amino acid sequence of the biological protein sample, is destructive. So this machinery, mass spec, will just destroy the sample during the sequencing process. So once you feed or once you get the result, you cannot get the protein sample back. So you can operate on it only once. Also, this machinery requires a pure enough protein sample to give you an output. And even that output, it could be either 0 or 1, meaning that it is either nothing or it will tell you the sequence of the protein, and that sequence, of course, will allow you to decode the message. And keep that point in mind for the protocol that I'm going to show you in a few slides. Based on these observations, we developed a novel protocol to allow us to store data in proteins in a way that achieves unclonability and self-destruction. And this protocol allows us to build what we call consumable memory tokens. As before, you take the digital message and you produce the protein material that represent this message. However, we combine this target protein with another shorter protein sequence called a header, such that this header is recognized by the matching antibodies. So if you have the description of the header, even in a digital way, this will allow you to identify the antibodies. Either you already have them, or you synthesize that description into the header and raise the antibodies that you will need for later. So then we take this target protein combined with the header and mix it with a large or a huge actually number of proteins that have identical physical properties, but all of them are combined with random headers that are different from the one that is tied to our target protein. And in essence, the target protein, protein M in the figure, represents the message payload, which is the secret message that you want to store. And the header, and of course, once you know the header, you know the matching antibodies, this represents the secret key tied to that message. So in essence, without knowing that secret key, you will not be able to retrieve the message from this huge mix. And the vial containing the mix of these proteins, which our co-author Anna is holding in this photo, represents our biological consumable token, which is the bounded query memory device. Now, to retrieve the secret message N, you need first to purify the sample that you have, and this can be done by applying the matching antibodies to the secret header. The antibodies that match the secret header, apply that to the sample. This will allow you to pull down the target protein. After that, we cleave the header and we feed the pure sample to mass spec, which will tell us about the sequence of the amino acids representing that protein. And that can be decoded to produce the digital message. And remember, whatever you feed to mass spec, it will be destructed, so you cannot operate on that sample once again. Also, we introduce a variation of our protocol to build what we call partially retrievable memory. So instead of storing a single secret message in the vial or in the consumable token, we store V messages. Each of these messages will be combined with a different random secret header. So you have a set of secret keys instead of one, which is V keys. And the unique thing about our token, which we formally call 1NV consumable token, V stands for the number of messages that you want to store, which can be one or any constant number you like. And N is the maximum number of queries that an adversary can perform, while 1 is the number of queries an honest or an honest party will perform. So in essence, the honest party knows the secret key, will apply it to the token, get the secret message. And it will choose only one of the N messages based on what she wants. The adversary could be more powerful than the honest party, and we account for that in our model, in the sense that it might own, advanced mass spec machinery that the honest party doesn't know of, or even us, we don't know of. And this will allow the adversary to operate on the sample more than once, in the sense that imagine that it will be split into several smaller samples, and this will allow the adversary to do more than one query. Nonetheless, the adversary cannot perform more than a prefixed number of queries that we denote as N here. Also, the nice thing about this construction is that even if the adversary knows all the secret keys, this will allow him to retrieve only N messages, but not all of them. And actually, we utilize that fact in one of our applications. Another thing to keep in mind is that with each retrieval query, a part of the token or the sample will be consumed. So after the N queries, the whole sample will be gone and there is nothing left to operate on. And from here, the name consumable we use with these tokens. After months and months of developing that protocol and understand the features of biology and how to deal with the unclonability and the self-destructive feature of proteins, we spent even more months in order to develop formal model to capture the features that represent our biology model in a mathematical way that allows us to use this functionality in advanced cryptography applications. Maybe I mentioned that earlier. Our goal was to request or to require the minimal on the biology side and leave any amplifications or strengthening on the cryptographic side. And due to all the limitations in the biology realm, the model that we have or the tokens that we have, they are weaker than what we wanted. For starters, a token can store only a small number of short messages. So this N cannot, or this V actually cannot be that large. And the keys are short, which means that if you want to store longer messages, then you have to divide the message into several parts and store each part in a separate token. The only meaningful interaction with the token is by applying antibodies or keys. And this is due to the way that the token is designed. So it is mixed with a massive set of proteins, all of which they are very similar in their physical features, so you cannot tell them apart. Also, each retrieval attempt will consume a part of the token or the vial, as I mentioned, and the adversary could be powerful and might be allowed or capable of performing more than one query compared to the honest party. And lastly, to account for all the inaccuracies on the biology side and the fact that sometimes you apply the wrong antibodies that don't match the header, but somehow you manage to pull down the protein tied to that header. So in math terms, you are applying the wrong key and still you are able to decrypt or to reveal the secret message. This case, we call it, or it is actually related to the soundness error, and our consumable token has non-negligible soundness error. There is a chance that, which is gamma chance, to get the message even when using the wrong header or the wrong secret key. And at that point, before continuing, because it's nice to show the construction of a consumable token, but what is it useful for? At that point, we put our cryptography box on the table and we asked the following question. Can we amplify the weak properties of this consumable token that allows us to deal with constant, even small size data to build strong, sophisticated cryptographic applications and functionalities that can deal with arbitrary size data? And answering that question took us a long journey. First, we modeled biology dealing with vials and all these biochemical procedures. We modeled them in terms of vectors and operations on these vectors, and we call that the vector model. So in essence, we look at the vial as a vector of protein quantities and concentrations, and the index of the vector represents the key, which is the header tied to that particular protein. And all the biochemical procedures, we model them as algorithms or functions applied to the vial, which is a vector in our case. Then based on that, we formalized an ideal functionality for consumable tokens, which include the interfaces and the security properties and guarantees. And this ideal functionality is the way to use it while proving security of the advanced applications. Also, we developed several algorithmic and cryptographic amplification techniques to allow us to use these weak tokens in advanced applications. In the work that I cited, we built two applications that I'm going to talk about them briefly in the remaining time. The first one is called digital lockers, and the second is bounded execution software. So let's look at the first one. A digital locker, if this is a term that you hear for the first time, it is a way for us to encrypt secret messages or a secret message using a low entropy password. All the time in encryption, and even like in all cryptographic applications, you have to pick your key to be long enough and random enough so it cannot be guessed easily by the adversary. And passwords, as we know, all the time, we have the problem that, humans tend to use weak passwords that can be guessed very easily. So digital lockers is a way that allows us to do that, encrypt with low entropy password. And this notion was put forward by Kaneti and Dakduk, who showed a construction that is secure for all attackers except against brute search attacks, because we have to accept the fact that the password space is small and you can try passwords from there until you decrypt correctly. So we asked the question, can we build even stronger notion of digital lockers? So yes, you are encrypting with a password, but the adversary who doesn't know your password can make only a few guesses. So just do a few encryptions, after which the whole locker will be gone, so we can resist brute search attacks. And in cryptography terms, this corresponds to what we call bounded query point function obfuscation. So it is a function that will output nothing or bottom for all incorrect passwords and will spit out the secret message for the correct password. And this could be very useful in access control, which allows us to restrict the number of logins that you can do in an interactive way. Now, what we have, usually there is a server sitting in the middle, and for each login trial that you make, this server will check if it is correct, will let you in, it will not allow you to access. And this server is counting the number of queries that you make. So after a few trials, it will lock you out. But again, this is interactive. You are interacting with the server, and with our tokens, you can do that in an interactive way. Again, the honest party who knows the password will make one query, get in, but the adversary who doesn't know the password can make up to n password guesses, after which no trials are left. And we construct that from consumable tokens. And you might say, by the way, this is so immediate. Your consumable token gives that functionality out of the box. Yeah, the secret message M is stored inside the token, and the password is mapped to a token key. If I try to access this message using the password, which is basically using the corresponding key, I'm going to get it. Otherwise, the adversary can make only up to n guesses. However, this doesn't work because we have this inaccuracy or the non-negligible soundness error. So the adversary might try incorrect password and still gets M or gains access. I'm not going to enter into the details of how we handled this. I'm just going to talk about it briefly, and please feel free to discuss offline or even ask about it later if you want. But basically, what we ended up doing is, instead of having one token containing M, we have U tokens, and each token contains a share of M. So we secret share M into U shares. And in order to get M, the honest party and the adversary must get all the shares from all the tokens. Also, we chained these tokens together to force everyone to work on them sequentially, and to address the fact that by sending you more tokens, we are increasing the number of queries beyond n. So with this chaining trick, we limit the number of trials back to be n, and we make the soundness error negligible. So the chances that you get m with incorrect password or incorrect key is, after the digital lockers, we looked at bounded execution software. And due to the power gap between the honest party and the adversary, as I mentioned before, the notion that we are able to build is called one-n time programs. In essence, it is kind of like a hybrid model between the one-time programs and the k-time programs. So again, this program could be secret or contains some secret state or secret information. The honest party can execute it only over one input and gets one output. The adversary can execute that program over up to n distinct inputs and get n outputs. After that, the program will stop responding. As a motivation, you can think of, for example, signature delegation for cryptocurrency wallets. I want you to spend some currency out of my wallet, but clearly I don't want to give you my secret key. I can construct a one-n time program, or in the ideal case, it will be k-time program, containing the signing algorithm and my signing, which is secret key inside. And for you can sign up to n transactions or one transaction if you are an honest party. And after that, you cannot use that delegation or that signing algorithm any further. And of course, you can imagine more and more applications of this notion of bounded execution. So we built this weaker notion of k-time programs using consumable tokens. And the idea at a high level combines what we call obfuscation and particular indistinguishability obfuscation with our tokens. And the idea is as follows. The program will be obfuscated, so you will get an unintelligent version of the program that it cannot be reverse engineered, or just like you cannot expose anything about the secret information inside it. And for you to run that program, it is not only that you have to provide the input, which is X in this case, but we ask you to provide another secret, unique message corresponding to X, which is M. So you'll be like, hey, execute F for me over X. I'll say yes, but show me the secret token or the secret value M. The secret value M is stored in the token, in the consumable token. And you can imagine it in the sense that for all the set of inputs, for each input, there is a unique message. All these unique messages are stored in the token. The honest party will be able to retrieve only one of these messages, which corresponds to one input. So it will be able to run the program over one input, while the adversary will be able to retrieve up to n messages that correspond to n unique inputs, meaning that it will be able to execute the program over only up to n inputs. The unique messages for the rest of the input space will be gone because the whole vial will be consumed after performing the last retrieval query. And at this point, you might say, okay, wonderful, but remember, you told us that your token can store only a few number of secret messages, meaning that we can only use this construction to deal with functionalities or functions that have a small input space or small domain. So how about programs with large input space? To address that, also I'm going to mention this very briefly, we utilize linear or error correcting codes where instead of dealing with the input directly, we encode that input and interact with the code word representing that input. And now we ask you to provide a secret unique message for each symbol in that code word. So now it is not only, hey, provide me with one message corresponding to the input, it will be provide me with omega messages or unique messages that are secret corresponding to the code word of my input. And to allow this larger space, we send omega tokens instead of one. And as you see, the code word will be a combination of the messages from all these tokens. And this will allow us to handle input spaces of exponential size. Also, we configure the code distance of the error correcting code in a way that only n valid code words can be retrieved from the tokens, meaning that the adversary can execute the program over only n inputs or distinct inputs. And of course, if you don't have the messages from the token, the program will not respond because this is the first condition that the obfuscated program will check before doing the execution for you and providing you with the output. And yeah, again, this is a high level of the idea. The paper includes even more details because we explain the idea first with a strong notion of obfuscation, which is virtual black box. And then we show how to use indistinguishability obfuscation, which is a little bit weaker, to construct the one-in-time programs and show, of course, all the proofs and whatnot. In this work, to conclude, we showed the world construction of unclonable and self-destructive memory devices. We provide formal treatment, modeling, and even we show provably secure cryptographic applications showing the benefit of these memory devices. For our future work, it is on two fronts, the biology side and the cryptography side. Now, the biology, we are still in the process of having the full biological construction, having empirical results, even quantifying all the parameters and the adversary power that we have in our model. And on the cryptography side, we are refining our models and exploring building more applications using this notion of bounded query memory devices, or what we call consumable tokens. This is it for today, and happy to take any questions.
Wow, wonderful. That was a lot more than in our previous workshop presentation. And I'm sure you also made a ton of progress since then. So thank you so much for sharing this. That's a lot. And yeah, are you ready to take questions, or do you want a brief break? Or you ready to?
No.
Okay, cool.
Yeah,
we already have two in the chat. So maybe David, if you want to unmute first.
Sure. So I feel like I'm being unfair asking bio questions to the crypto person, but how stable is the DNA that you're working with? How difficult is it to actually work with the system?
So yeah, I will try to answer as far as I understand. Okay. And yeah, as you said, I'm a cryptographer, but trying to educate myself here. First of all, we deal with the proteins, not DNA. And for the stability side, this is the reason why we can encode only short messages, because when you start dealing with longer messages, proteins start folding and whatnot. Also, we don't use all the amino acids that are out there. We were forced to omit a few of them due to that stability reason and to allow reading kind of like in more accurate or in a better way. Also, I have to say, still we have a long journey in order to have the final product on the biology side. So yeah, in theory and the preliminary results that we have, so we managed to store short messages and read them. Things are so promising. But when it comes to looking at longer messages that are random, that the header aspect, reading proteins in that sense is way harder. So usually reading proteins comes by matching databases that you already know with the protein sequence that you have. And that one doesn't work for us because the message is secret. It is not supposed to be, okay, in some database and you just look for it. So yeah, things are harder than we imagined. And it is taking us longer than what we anticipated. And yeah, of course, also thanks to COVID, where our biologists get distracted with kind of like the vaccines and whatnot for a while. And just like recently, we went back on track for this aspect.
And thank you.
Okay, wonderful. I think that was a great question for a great answer for a cryptographer for the biology question. Alan, you're next.
So normally in password systems that have a limited number of guesses, an attacker can mount a denial of service attack, simply locking the legitimate user out. I asked a question here, but I think I thought of the answer. In this system, I can submit a vial with my password. If the attacker does enough guesses that destroys the vial, the data in the vial, I can just submit another vial with the actual same password in it. And so this attack cannot be used. The denial of service cannot be used. It sounds, is that right?
Yes, so your intuition is right. And the adversary that we're looking at here, which is also a feature of the model that we have, is one who manages to steal the token. Imagine, because all the time, this process involves going to a biology lab, tell them what to do, and they will create the token for you or the vial for you. So if on the way back, the adversary managed to steal that vial, so in a sense, he managed to steal the way that will allow you to get in or access the system. But yeah, that adversary will have only limited number of trials and the whole token will be gone. And exactly what you said, if you realize that, either you can change the password or even have them send another token. But of course, sending another token, if the adversary manages to steal it again, now he will avoid the wrong guesses he made from before, and he will try to make new guesses. So it's better to even change the password at that time.
Feel free to answer to that, Alan. I know that you just raised your hand.
Yeah. Another thing might be an added protection. Heat can destroy the proteins. So that perhaps there's a way to put this in a device that if it's tampered with, it will destroy the proteins and thereby the message.
Definitely, this is also another great intuition. However, our goal is to avoid having these additional tamper-proof devices and start, again, just like the manufacturer trust and whatnot. So our goal is just to look at the vial itself. It's stored in I'm not going to say the perfect, but the suitable environment conditions that the protein will not be spoiled, which is another great point that like implicitly you mentioned. So even the honest party has to store the vial in good environment, otherwise it will be destroyed. So even herself will not be able to use it. So yeah, our goal is we are just dealing with these proteins, with these vials, without additional protection on the physical side that will require us to trust someone else other than the biology.
Of course, just a thought. Thank you.
Of course. Thanks.
Cool. David had another question.
Yeah, following up on that one, I guess if you're using the password to validate who you are, then presumably you can't just show up and hand them a new vial and say, oh, actually, I want to check against this password because you haven't validated who you are. Like the threat model here seems to preclude that solution, where if you can validate who you are without providing the password so that you can give them a new vial, then you don't need to, you've solved the problem you're showing up to deal with. So it does seem, and the other place that you would want to use this presumably is where somebody wants to anonymously attest to being the person who originally said something. So like in those cases, if somebody gets to try multiple times and they destroy the sample, then you're out of luck. So I guess the question is, when you're designing these protocols, would you explicitly try and attempt to limit how many queries any one user would make to a number much lower than n? Or like, how do you actually use this in design?
A great question. So about the identification or the access control, yeah, I have to say this is just an example that I use to make the idea closer to mind, but the actual application itself is a little bit more involved in the sense that we look at it as a way for two parties to exchange secret data without having any infrastructure other than sharing a password. So usually we say, oh, I have a secure channel between me and you, and we exchange data, and this secure channel, we know that to build it or instantiate it, it needs so many protocols beforehand. So here, just assume that we have Alice and Bob. Alice and Bob only shares a password, and Alice later wants to send secret information to Bob. It could be some signed message or even some secret key to be used for something else, and so on. So by having Alice preparing the vial and sending it to Bob, Bob now can access that information or that secret information only if he has or if he knows the password. And any adversary sitting in between who managed to seize the token will be able to try it like a few times, and after that, no luck, he cannot try any further. So this is the way that we look at it, how these digital lockers can be useful in practice, which is a way, if you want to call it, password authenticated interaction or communication, rather than the very strong, which is key authenticated interaction that we usually have. And the number of queries, of course, this can be done at the biology side when you are building the token. So the amount of proteins that you put in the vial will control the number n, which is the number of queries that an adversary can make. Nonetheless, we also account to the fact that we might not know the full capability of the adversary. So even if we envision that, okay, this little amount is enough for 5 queries, for example, the adversary might have more advanced machinery that will allow him to do 7 or 8, but definitely not larger by much, because still you have all the limitations on the physical properties and even the reading of the protein itself.
For this, then, it seems if you have a man-in-the-middle attack where somebody has tried a password or two before you get it, you should be able to detect how many attempts have been made based on how much of the protein there is.
Yeah, definitely. You will know immediately that the protein, the sample was tampered by. Basically, it's because you will not be able to use it. So the protein, the original amount is enough for 1 query for the honest party. So this is kind of the way you need to imagine it. So we know the capabilities of the recipient, and the token will be enough for 1 query. If the adversary just operates on just like portion of it and then pretends that nothing happened and return the token to the recipient will know, because the amount is not enough. You will not be able to authenticate or just like to access the secret data. Yeah, that's true.
You feel good, David? Wonderful. Well, I have a few perhaps more general questions, and it's also just like you can still raise your hand, but I'm really like at Foresight, I guess we're always interested in the more kind of like speculative in the future, where could this lead? And I already love that you put in future work, biology and cryptography. And I would love to see if we can maybe dig in a little bit more into both of those. I mean, the biology part, I don't know just like how much you can say on that really, but if you could just kind of lay a path out there on like how the kind of like full biological constructions could work, or like any challenges that like are currently preventing progress from occurring there, because I think that could also be interesting for people watching this. And then maybe we tackle the cryptography part after this. But if you have any further ideas on the biological kind of future work implications, and that would be great. Like any kind of like things as a biologist, for example, let's say I come across this presentation, like what would you want me to like work on, or where would you want to?
Yeah, on the biology side, I think the current challenge that we have now is accurately reading or sequencing proteins that are simply random proteins, represent random messages. So we have difficulty there, because the success that we have now is still, it just shows visibility, but not even to the levels that we want. And in fact, we are actively looking for collaborators who are experts in mass spec and de novo sequencing or reading to help us with that. The other challenge there as well, which comes actually as, you can say, side effect, but this is how life works, I guess. When you have people coming from different fields, they have different terminologies. Basically, they speak different language, although it's still English, but it's very different. And convincing each other that this matters or this doesn't matter is a little bit hard. So even to us, it was hard to get the biologists on board that, oh, there is an adversary who's interested in this or that. It was a little bit hard, and the other way around. At the beginning, oh, can't we do this? And can't we do that? And it took them a while just like to explain to us that this is not just magic. Yeah, you can put theories as much as you want, but you have to prove them and show them in the lab that they are working. Yeah, this conversation will lead to, okay, how to examine the biology protocol in terms of its resilience to adversaries or attackers. What are the exact limitations that we have? So now we have just like loose bounds, but we want kind of more accurate ones in order to use them in our model and so on. So it's kind of both on the experiment side and even on designing these experiments in a way that will reflect the theory model that we have. So yeah, so that's on the biology. On the cryptography side, I'm not going to say it's easier. It's just I feel it easier because this is my field. So the model that we have now, it has several simplification assumptions in how we model biology and what we assume. We would love to strengthen this model by relaxing these assumptions and have them to be more realistic, closer to biology and how things work in practice. Also, some of the directions that I'm very interested in, and just get a recent short paper on that topic, which is exploring how we can combine the unclonability principle that we get from proteins with the unclonability principle of quantum computing, and see if combining these together will allow us to have maybe a stronger model that will allow us to build even newer applications or primitives that we didn't know of before, or we know of, but we couldn't build from just the classic model or just quantum alone before. And of course, even here, I am not a quantum person. So again, we need to find collaborators, even with the open mindset that, hey, there is something crazy called building cryptography from proteins. Let's see how to combine it with a quantum. And quantum itself is still challenging. Yeah, it is way more advanced compared to biological polymers and their use in cryptography, but you cannot consider them as mature as the classic model that we know. So yeah, to me, I guess these are the challenges or the obstacles on both paths. And yeah, it might be a long path to achieve these, but I think it's worth it.
Very cool. Well, I'm just trying to go already on the call here through our list of like protein people to see if someone could be like adventurous enough to like at least take on the biology bit. But if you have any specific kind of like requests for collaboration or something to share, we can share it in our molecular machines group, and maybe we'll have a few takers there. I can imagine a few of them will be like game for this type of stuff. But I think that's always the problem that you mentioned. Yeah.
Yeah, definitely that would be great. Yeah.
Okay, cool. Yeah, please send anything my way. But I think it's always so difficult. People always say they want it in disciplinary collaboration, but then when you try to make it happen, just even understanding either the tools that are being built in a field or the problems that another field is solving, especially I think the cryptographic problems must be a lot to explain, I think, to biologists or like to chemists or to, yeah, that's crazy. Okay, very interesting. And on the application front, I'm super curious, like how long do you see the timeline, for example, from like research to, let's say, like application in a more, not really, maybe not very much like a mainstream setting, but for those who are potentially using that, like that version of cryptography, like what's the timeline here? I have no idea how long this would actually take to like properly implement.
Yeah, I wish I have answer for this. I wish I can say, oh, I know in the next 5 years or the 10 years, because part of it, pretty much, this is an answer on the biology side rather than the cryptography side. So even this work, it took us almost 4 years, but of course, COVID interrupted and slowed down the process. But during these 4 years, yeah, we were able to do a lot on the cryptography side, but on the biology side, it was way less. And even since the beginning, we required the minimal from the biology side, but even that one, it took us longer than what we expected. To build more applications, I think one of the notions out there is called unclonable cryptography, where people started to look at all the cryptography that we know and see if there is unclonable version of it. I don't know, a ciphertext that can be decrypted once, an encryption key that can be used only once, k times or n times, and so on. So these, even in case like for these applications, still people find difficulties in imagining, okay, where could this be useful beyond just being a cool theoretical concept? So even on that front, I think that there is also a long path ahead to find mainstream applications where we really believe that, okay, such notions or primitives will be useful. Yeah. Again, I wish I can provide a timeline, but yeah, perhaps one of my biology collaborators here might be a little bit more specific, but still not that specific, because we don't know even the current challenges, when will they be solved, and what these challenges will produce more. Maybe, I don't know, there will be more challenges down the path that we don't know of now.
Cool. Do you have any like kind of hot takes or something on how any of this may interact with like AI progress? We are, for example, launching like a new AI safety grant category on cryptographic security and auxiliary approaches for AI safety. And I'm super curious. I mean, this work in itself is still perhaps like a little bit further out than some of the shorter AGI timelines.
Right.
I'm really curious if you see any connections there.
Yeah, maybe I'm going to provide connection based on how I see things, okay? Because, yeah, I'm not an AI expert. I worked a little bit on privacy for machine learning, so maybe I can answer based on that. One of the things there, I guess the concepts that we develop here would be useful for delegation, in the sense that you can delegate the inference, or which is running a model over a particular input to see the prediction. You can delegate it to the client in a secure way. So the client will not be able to see the model, but still they will see the prediction. They cannot run that prediction more than once, or I don't know, n times. And this will provide security for both the model owner and for the client. Also, it could be the case that these constructions will be useful for anonymity purposes, where clients can participate in, I don't know, a learning or even inference task or kind of activity without revealing who they are. And this is actually a critical problem, in the sense that many people out there, they own invaluable data sets, but they are not willing to share. Part of it because they don't want to be known, I don't know, they are ill with some particular disease, because just participating in the process, it means that, okay, you have a data set of that type, so we know some information about you, even if we don't know who you are. So I think having this non-interactive bounded query execution might help with solving these problems. But yeah, of course, it's like this is just an intuition or high-level direction, and yeah, the details could be more involved.
Interesting. Okay, let me ask Charles Bollum's question here in the chat, which is, it would seem that local fabrication of the biological agents is a requirement. Sending the secrets to an external lab exposes them. How likely is it to build a machine that can automatically create the samples?
Yeah, this is the dream, I guess, because yeah, until now, the biological lab is one of the entities there, and we assume they are honest. So this is how we look at it. So once you say, okay, create a token, you know that those guys will follow the protocol exactly as it is described. They will not leak the message. They will not leak your key, and so on. But yeah, again, I wish I can even just provide some hints about this, but I imagine it's a very hard thing to achieve. But yeah, hopefully in the future, it will be something, just the DNA sequencing and desequencing. It will be small device. You can just plug it into your laptop, and you can feed it with your secret message and get at least the sequence on the other side that can be synthesized for you in the lab, rather than having the whole process being done in the lab itself.
Yeah, I mean, I definitely know that like in our biotech group, there's a lot more discussion on like more, just like a lot more local fabrication of any specific like interventions or sample selection or like activation that you may want. So perhaps that's not too far away. Okay, final question, because we only have 1 minute left, which is, if people are excited about your work, how can they help support you? Either specific collaborations, I know that we talked about a few of them, but if there's anything else, this is like a shameless plug moment where you can just kind of share any specific kind of like bits that are holding your particular research.
Yeah, so to me, maybe now the collaboration thing, because once you find the right collaborators, you can even explore more in the sense that, okay, these things are super expensive, or this research to conduct it is super expensive. Can we get more funds and whatnot? But I guess all of that is just a follow-up of finding the right collaborators, the right minds to think about the problems, the path forward, and so on. So yeah, I guess to me, this is the critical thing now. Not to say that, okay, getting funds is super easy, but once the right talent is there and the right ideas are there, things get easier. So yeah, what I'm looking for, basically collaborators and even just chats or conversations that will help in shaping the future of this work will be very helpful.
Well, I mean, we'll definitely try to make sure that we share this presentation in our other technical groups as well, so they even just know that this exists as a problem area they could be solving. And anything more as concrete or specific, please also send my way. Thank you so much for joining us. This was really fantastic, wonderful, very exciting, novel, and really cool. Thanks everyone for your great questions. And I'm seeing you, I think, next week for those of you who are interested in joining our AI safety launch event. And so thank you so much. I hope you have a wonderful rest of your day. Thank you for joining.